So in this video, I want to take a look at how to differentiate another kind of function. It's not like a specific function like a trigonometric function or a natural log function, but I want to take a look at a classic example of a function. Let's say that I have not really a function, but an equation. I have x squared plus y squared equals 1. I have not really a function, I have an equation. And you would know that if you were to look at this equation, you would know that that is the equation, that is an equation of a circle. But more importantly, that is an equation of a unit circle of radius 1. And we can pretend that we can get that as close to the center as possible, and that this distance is a radius of 1. And so this is what the equation would look like. It would be an equation of a unit circle with radius r equals 1. Now what I want to do is I want to figure out, okay, what is the derivative of this equation? Now you might notice that this is a bit of a problem. We can't really do this because normally we've dealt with functions written explicitly. We've normally dealt with functions written explicitly. I don't know that that's how you spell explicitly. Oh well, that's gonna be how you spell it right now. Maybe there is no e. It maybe just be TLY. That's probably how you spell it. I don't know how to spell it. I'm not gonna look it up. But anyway, you get what I mean. We're used to functions defined explicitly, where y is explicitly defined as a function of x, like y equals x squared. That's an example of an explicitly defined function. But we noticed a little something here. We noticed that over here, this function is defined. I'm actually going to label it over here so we can keep that label on screen. We notice that this function is defined implicitly. Implicitly. And we have never really dealt with functions that are implicitly defined. Now, how could we find the derivative of this? Well, we could isolate the variable for x. We could isolate x, and so we could get, we could isolate y, because then y would be a function of x. So we get y squared equals x squared plus 1. And then if we were to take the square root of both sides, we would get that y equals the positive or negative square root of x squared plus 1. And now y is written as a function of x. And we could take the derivative of that, but again, that derivative could be hard to find because we have both a positive and a negative answer, so when we take the derivative twice, like what would that look like? And in this video, what I want to do is I want to show you a different way to calculate the derivative of a function defined implicitly. And in fact, it actually is super, super useful and super, super helpful, because then we don't ever have to actually write each function, because some functions that are defined implicitly, you can't even really write them in an explicit form. So there's a way that we can take the derivative of this. Without having to isolate the y variable. We can still take the derivative even though the y is mixed in with the x. So what I'm going to do is I'm going to do something that we're kind of been used to and we've been doing this whole time. I'm just going to take the derivative of each side of the equation. I'm simply going to take the derivative with respect to x, because that's what we always do. We're going to take the derivative with respect to x of each side of the equation. And of course, the reason we're doing it to each side of the equation is whatever you do to one side, you have to do to the other side. So we're going to apply this derivative. We're going to differentiate each side of the equation. So we'll notice if we were to continue simplifying this, we would get d dx times x squared. So we'd get d dx x squared, and we would get plus d dx of y squared, d dx of y squared, and that's going to equal, d, I did dy dx over here. I didn't mean to do, we don't need that y. It's not dy dx. It's simply d dx. There's no dy. My bad. Sorry if that was confusing. And d dx of 1. And what does this simplify out to be? Well, we know how to take the derivative. Let's do what we know. Let's do what's simple and we can understand. Well, we know that the derivative of any any constant, you see this is just the derivative with respect to x of 1, and the derivative of any constant, be it 1 or another constant, that's simply just 0, so we can write in a 0 there. What else do we know? Well, we can do this term, too, the derivative with respect to x of x squared. Well, that's the power rule. We're going to bring down the power in front, and then we're going to multiply it by x times the n minus 1 power. So I'm going to subtract 1 from this power, and 2 minus 1 is 1, so that's just 2x. I'm going to leave it like that. But what is the derivative with respect to x of y squared? Well, we haven't really done anything like that. So let's take this term and do a little bit of, oh, I did not mean to do that. Let's put that back. I did not mean to do that at all. I didn't want to cut it. I just wanted to take it, and I wanted to copy it and put it somewhere else where you can do some manipulation. So I'm going to do it in the bottom corner of the screen over here. And I see that d dx of y squared, well, I noticed that this is a chain rule. Remember, y itself is a function of x. Y itself is a function of x. So if we were to take the derivative with respect to x, if we were to simply just do that, I'm going to need to do that somewhere. I'm going to need to make space. I don't know that we really need, I think we want this, all of this stuff, all this business, but I don't think we need, like, I don't think it needs to be so nice and big. So let me take this and let me shrink it, kind of move it up to the side here so we have room to work with some stuff. So maybe I'll go ahead and paste and then do this right here maybe, and then let's see, maybe then get rid of this, and then sorry about this, guys. But let's say we wanted to take the derivative with respect to x, the derivative with respect to x of y. Oh, I don't want that to be white. I want the, there we go. The derivative with respect to x of simply just y, well, that's going to equal, that y is just going to be multiplied into the numerator. So we're just going to get dy dx. And we've seen that before. We've seen that the derivative, we've seen this dy dx. We're wanting to find dy. In fact, when we take the derivative of anything, we're looking for dy dx. So this is important. We want this to come up. This is good. This makes us happy. We want this to come up. That was a terrible smiley face. Wow, if I drew a smiley face, I've got to draw a good Trevor. We got to draw a good smiley face if we're drawing smiley faces. Okay, so then what would be the derivative with respect to x of y squared? Well, that's just the chain rule. We're just going to use the chain rule, because we notice that we have a power function. Because y is a function of x, this is the only reason why it's the chain rules, because y is a function of x. So we have a function of x right here, and then that function of x is being acted upon by another function, in this case, this squared function. So we really have this being our outside function, and this y, this function of x, is our inside function. So we have a quadratic function as our outside function, and a function of x as our inside function. So when we implement the chain rule, we're going to bring the power down front and decrease the power by 1. So it's going to be 2 times y to the first, or just 2 to the y. But then we're going to multiply by the derivative of the inside. And the derivative of the inside, well, what's the derivative of y? Well, we just found the derivative of y up here. The derivative of y is just dy dx. And so this whole term is going to end up being 2 times y times dy dx. Now again, we want to find this derivative. We want to find what dy dx is. Normally, we always want to find what this dy dx is. And so in this case, when we want to find the derivative with respect to x of this giant equation, we're going to want to solve for dy dx. Let's go ahead and do that. Well, if I wanted to solve for dy dx, I could subtract 2x from both sides, and if I did that, I would get that 2y dy dx is equal to negative 2x, and that, again, that would happen if I were to subtract 2x from each side. These 2x's would cancel, and that's what would happen. And then I'm going to finally I'm going to divide by 2y, and if I divide by 2y, well, the 2 and the y's are going to cancel, and the 2's are going to cancel here, and I'm simply going to get that dy dx is equal to negative x over y. So now we found this. Remember, this function, we defined it. We defined that function implicitly. It wasn't an explicit form of y equals x. It was defined implicitly. But we were still able to find what dy dx was equal to. Now it's expressed implicitly in terms of x and y. This is the correct way to differentiate. We call this method of differentiation, we call this method implicit differentiation. This is the big topic of this video. Implicit differentiation. That is the big, I don't want to cross out everything I've just written. That is the big idea topic that we talked about in this video, implicit differentiation. And so I'm going to do another video, a separate video on an example on implicit differentiation, so I can teach you, we can do a more complicated example. I can show some tips and some steps to solve these differential how to differentiate in implicit equation. But for now, this is just the basic intuition of what implicit differentiation is.